Well, this is week 6, lecture B. Today we are going to focus on Bode block, okay? And before that, I'm going to tell you the last Wednesday's quiz. Please spend 3 minutes focusing on this one and do it on your back of the quiz for the first time. You have quiz B for today. We are going to work on it together. I'm going to draw on the board and you are going to draw on your quiz, okay? Write down your name, it's very important, and make sure today's lecture you are not going to miss. Okay? Do you need more copies? Okay, so for the quiz, basically we have some magic words in here. Can you see IVT, FVT, final value theorem, initial value theorem? Please, we need to turn this one off. Maybe it's better. Okay, let me recap what we learned last time. We are talking about the system's response in time domain or in frequency domain. So in time domain, of course, your x-axis is t. In frequency domain, then your x-axis is omega or f. Okay. By the way, omega is 2f. Okay. 2 pi f. Okay. Omega is 2 pi f. So when we say omega, is as if we are saying f. Okay. So you need to think about, I have a sinusoid applied to the system, while the frequency of the sinusoid could be kind of sweeping. Okay. It's changing from low to high. Then we see how the system output changes. On one side, the output will never change because, remember, say with me, sine in and sine out. Omega is the same. The difference is the output with amplitude and phase different. And that amplitude and phase differences are functions of omega. So those amplitude and the phase change over omega is called frequency response. So specifically, we are going to learn how to draw manually the Bode plot. It's a frequency response using a specific method about using x-axis is log 10 omega, and the y-axis is 20 log 10 amplitude a to the omega. Okay, so this is called this is the phase. Okay, omega. As I said, I have a system. You have sine omega in. I have sine omega out. Okay? But this sine omega out with a different amplitude and with different theta. Okay? Different theta. And this amplitude is function of omega. The theta is a function of omega. Make sense? Then this is a function of omega. Function of omega. So these two are called Bode plot. It is a special form of representation of frequency response. But if you wanted to say it 100% correct, you should say frequency domain. Frequency domain response. Okay? Or previously we talked about time domain response. Okay? In a time domain response, basically you have a sinus, you have a like S plus A, S plus B, S plus C. So then I have step is 1 of S, Y of S is U of S is 1 of S, right? This is my U of S times the GS. Okay, the GS is S plus C, S plus A, S plus B. Okay? So I told you last time we need to use a shortcut, it's called copy. Cover up and plug in. Cover up and plug in. Okay? So then it's much easier, you can write a form, it's called PFE, partial fraction expansion. So you write K1 S plus K2 S plus A plus K3 S plus B. So what is the K1? What is the K1? When S is 0, then we cover up this. Insert S is 0 because the pole is 0. Insert is 0, so you C divided by A, B. So this K1 will give you C divided by AB. Okay? And you can do the same thing for K2. If you want to get K2, you cover up S plus A, plug in minus A, minus A, minus A, minus A, you get K2. I hope you will never forget this idea, okay? And also I said, when you have squaring here, okay, squaring here, then you have squaring here, plus you have another two term S plus A, K3, 2, and S plus B. Okay, so for getting these, you have to do derivative. Cover up derivative and plug in. You need to practice in the homework, okay? I already did one example for you. So don't ask me to do the second example, okay? Read the textbook. We also talked about stability last time. Everything is clear cut, left and right. Left is stable, right unstable. It's only related to the pole's position. But if you have something in the middle on an imaginary axis, so then it is called critically stable. Critically stable. But be careful when I say critically stable. When I say critically stable, that means you have only multiplicity as 1. If you have a multiplicity of 2 or above, that stability, critical stability is no longer there. It is unstable. Okay, it is unstable. So let's review that. So today we are going to focus on. You have a G of S in here. G of S in here. Of course, we write the G of S written in terms of numerator of S and denominator of S, okay? And this is a polynomial, okay? It's a polynomial. And I know that the degree, the highest degree of the D of S minus the degree of my N of S is called, a name is called the relative degree, okay? Relative degree of the transfer function. Usually, this relative degree is greater than 0. It's greater than 0. Meaning the degree of numerator is always less than degree of denominator. Okay? So, in that case, this transfer function is called strictly proper. Proper. So if this degree is higher than this one, then we call it is not so proper. It's not proper. Okay? It's not proper. Alright, so now we are going to do Bode plot. So by doing a Bode plot with this simple one, so you have a pole, you have a zero, you have a gain, and you have an integrator. This 1 over s is an integrator, okay? 1 over s is an integrator. So what's the step we need to do? The first step is to convert the PZK. So this is also called PZK format. Pole zero gain. Pole zero gain format. Okay, PZK format. In MATLAB, there is a dedicated command that's called PZK. Okay? PZK. So this is usually is a polynomial, but the polynomial is usually written in terms of sigma, like AK, SK, K, that's M, 0, K, 0, and it is a BK, SK. So this is a polynomial, right? This is a polynomial. This is a polynomial. So this is a polynomial. But we also can turn this polynomial solve its poles. I can write down like pi is a contact, is a product, okay? It's like s minus s plus zk, and you can do this s plus pk. So it's a zero pole. Of course, you can put a gain here. So this format is called, this format, you know, is a polynomial format, right? Polynomial format. Polynomial. Okay, but usually we put Bn. Bn is 1, and it has a name, it's called monic polynomial. Okay? But now this is called PZK format. So you have a system, okay? You have multiple ways to describe it, okay? Remember, we even had A, B, C, D, state space to do that, okay? Remember? Okay. So this is a graduate level course I'm teaching right now. Is ME210, linear multivariate control. So when you have an input is more than one, output is more than one, and what's the inner structure? How we can describe that, and that's the next step. But the PZK format, okay, polynomial format, ABCD format is steady space. Okay, steady space. So this Bode is called TF. Okay, TF. So if you go to MATLAB, SS is a command. Okay, TF is also a command. Transfer function, okay? So both of these will generate something called LTI object, linear time invariant object, okay? Object. But anyway, let's assume that we can do a PZK format. We have to use this format to do Bode plot. Otherwise, in polynomial format, you have no clue. I think the reason is very clear. So what we do is to do what they call standard form. What we do standard form is called S divided by J omega. S is a J omega divided by omega. So then this is something, well, unitless, it's dimensionless. So you move the z outside, okay? You move the z pole outside, so you always have 1 plus something, okay? 1 plus something, 1 plus something, okay? And so zeros and poles, you can have more. You can have more terms, but let's just for illustration, one term. So what are we going to do? So then we replace S with J omega, there's omega missing. So then we'll have a complex number. So this is my transfer function. It's already called frequency response. okay, frequency response. So you have a complex number here. This is a complex number, this is a complex number. So overall it's also a complex number in omega, in terms of omega. Omega is changing. And using omega as an x-axis to see what's going on. Then let's just do a log 10 of this, okay? Log 10 of this, you have this. Okay, this. So let's focus on the magnitude. Let's focus on the magnitude. So the magnitude will be k and log. So you have z here. So you have log k and you have z. So then all the product will be summation. And here, this is log 10 of this one, j omega z plus this one. And in the denominator is minus, okay? Okay, denominator is minus. So do 20 log 10, we have this one, and this one, and this one. So that's for magnitude. That's about magnitude. Is there anything new here? I don't think so. There is nothing new here, right? Nothing new here. So again, I asked you more than once to review complex numbers. If you are not very familiar with complex numbers, so these are complex numbers, right? So you have j, which is the square root of 1, square root of minus 1. So these are individual terms in the logarithm plot. So the entire Bode plot magnitude is a result of this superposition of all the straight line terms. So straight line, so this is not changing over omega, right? So it's a straight line. If you draw in omega, it's a straight line, okay, straight line. Then you just add a straight line or minus straight line. So these are minus. So we can quickly see each term, what's the effect, find the overall effect. So understand the effect of different types of terms in here. So this is a type of term, this is another type of term, okay? It's minus and plus. So if the numerator is plus, and then denominator is minus, okay? So we are going to clarify that. What is the constant term? What is the point 0 at the origin? So j omega term. So, and what is the point 0 not at the origin? What if I have a complex conjugate poles and zeros? Okay. So the first thing is, if we have a k term and 20 log 10k is nothing but a straight line, okay? Any question on this? Or if you see a question mark, that's some typo, not typo, some version means the incompatibility. This should be omega, okay? Omega is 1, okay? So replace question mark with omega. So if I have an individual 0 and poles at the origin, okay? Remember I'm saying origin. In origin means when this is 1, the magnitude of this one is also 1. Then I do a log 20 log 10. Log 10 1 is 0. So then this is y is 0, x is 1. Okay? So this is passing the origin. Okay? Passing the origin. Is s or j omega. Okay? So the origin will pass 0 and 1 point. Okay? But remember, when we do the log 10 omega, we usually say this is 0. So we should say this is 1. Okay? Okay. So then this is 0. Okay? 0, 0. Okay, this 0 dB is 1. Omega is also 1. Okay, it's a 0 actually. Or log 10 is 0. But when is a DC? DC is omega is 0. Then log omega 0 is all the way to minus infinity is DC. This is my DC actually. Minus infinity. Okay, be careful. Okay. Make sense? Okay. So pole at the origin will pass through the 1 and 0 dB here. Basically, it's 1, 1. Okay? 1, 1. The same thing if you put it in the denominator, you have this slope. And remember, what is the slope? The slope here is 20 dB per decade. Okay, this is 20 dB per decade, see my hand? And going, this one is minus 20 dB per decade. Drop of 20 dB per decade. Okay. So all this constant and passing origin, this is easy. This one is a little bit involved. Please be aware. Effect of individual zeros and poles not at the origin. If they are not at the origin, okay, not at the origin, then we are dealing with this one. Okay, we always deal with this one. So this is omega divided by omega, omega divided by omega. So this thing, this number, when omega equals this one, when equals to this one, that is called a corner frequency. Corner frequency. Corner frequency. Okay. Corner frequency. So when omega is Zi, this is corner frequency. This is corner. When omega is pi, so this is 1. So 1 plus J1. 1 plus J1. Okay. So this is pi, this is Zi. Okay. But when Zi greater less than pi, you are here. This red line could be like this, going up. Okay, going up. So you have 20 dB per decade is minus 20 dB. So this one will result in minus 20 dB per decade. This one will result in 20 dB per decade. Okay. So then these two will add. Okay. So this red one is for this only. This blue one is for this one only. And this one minus this one will be what's left. So you will see it will be 0, 0, then this one will keep going until to this constant, because I minus this one, so it becomes constant. Okay, so we'll see. What's the resulting edge? Okay, so the red one is the numerator, the blue one is the denominator. Okay, so let's go through an example. Okay, TF is my transfer function. So this is the first example. To do this one, what we should do is make it a standard form, like S divided by omega. So by doing that, divided by 100 both sides, you have K is 1 over 100, K is 0.01, P is 50. So then this K will be given the minus 40 dB, and the pole is critical frequency. I said corner frequency, he said critical frequency. Yes, it is P1, okay? Then this term will be J1 plus 1. J1 plus 1, okay? At this point, it's J1 plus 1. So I'm going to show you that the red one is constant. The green one is constant when S is 0, very small. So you have 1, that's 0. So this is 0 dB. Do you see that? This is 0 dB. So this dotted line starting from 0 dB is because of that. And they will turn down at minus 20 dB per decade, okay? Per decade. Okay. So this is the corner frequency. And then the red one is this one. So we use this one and add this one together. And we have this resultant black one. This black one is our final Bode plot. Okay? Bode plot. So you can see the frequency is 50, it's the corner frequency. This makes sense? So with that, you will be able to draw your, see the back of your quiz, back of your quiz, okay? We are going to work on that together, but you start to think about it. Okay? Start to think about it. So how to find out body plot of this one? How to find out? So you have S in here passing through the origin. So this is the second term. So how are we going to do it? Do you know how to do it? So this kind of paper. So in terms of dB, in terms of log, this is called body plot paper. Okay, body plot paper. There is a dedicated code can be used to generate that. So let's do this problem. Okay, so again, we happen to be able to make this one two terms, like two poles in here. We have two poles in here. So then we just make this one standard form becomes S divided by P1, pole 1, second pole, pole 2. And this one we divided by 5, 2500. So together we get 20 left. So this is what I have, okay? So clearly, when I have log 20 log 10, 20 log 10, 20, will give me 26.02 dB, okay? dB, this is the red line. I have 0 at the origin, so this one will pass 1, omega is 1, 0 dB, okay? This is 0 dB. So you have this positive 20 dB per decade, okay? So that's a 1, 0 at the origin. You go up. Okay. You have two poles. One is at 5 corner, and this is a 500, and this going down, and this one also going down. So then we get this 4. 1, 2, 3, 4. 1, 2, 3, 4. This 4 using just a superposition. Add them together. Add them together. Okay. Then what's the resultant? So these are the steps. You draw the line of each individual term on the graph. So this is the individual term. 1, 2, 3, 4. We have 4 terms. Follow the combined pole 0 at origin line back to the left side of the graph. And then you do a 20 log 10K. Move that. Then your pole 0 not at the origin, and then you know this is the case. So we'll see what's the final one. So remember, okay? Remember. So I have a 26 point some dB. That's the red line. This is the So this is the constant A. This one goes through the 1. So this is the 1, okay? So remember, this is this is the 1, okay? This is the 1. Omega is 1. Then this is 0 dB. So this one is S. And this slope is 20 dB per decade. So then there should be 2 decades in here. From here to here is 2 decades. From 0 to 2 decades. And here is 40 dB. So therefore, the slope is 20 dB per decade. This is 40 dB per 2 decades. Okay? So this is the first term, second term. This is S plus 1 over S plus 5. Okay? So the corner frequency is 5. So this is 1, 2, 3, 4, 5. So it's here. This is 5. Okay? So this is corner frequency, just draw minus 20 dB per decade. Okay? So you have 50. So this is 100, 200, 300, 400, 500, 500 here. And then going down. This one should be parallel. So this is all minus 20 dB per decade. Okay? Now we are going to add together. What's the resultant one is the resultant one is the black one. So let's check. So this red plus this one, because this green and this orange will always starting from 0 dB. Remember, 1 over S divided by P plus 1. When S is very small, then it's 1 divided by 1, right? So 1 divided by 1 is 0 dB, okay? Okay. So they all start from 0 dB, then eventually they start to be different. There's a turning point. That point is that P or 0, okay? The turning point. Great. So then we can add this one. So this point is 20 dB, okay? This is minus 20 dB. But this is 26, so this is 6 dB, okay? So this value here should be the same as this value, okay? Makes sense? So this one goes to, so from here to here is 26, okay? Otherwise, you go, if this is 0, then we just go from here. But this is not 0, so we just all floating up. So this line will get floated up to this one, starting from 6 dB. Until, because this is 0, this is until here nothing changes. So this one, until this point, okay, this point, okay, until this point. So this one, add this one, add this one, because this is still going up. If without this one, this is going up, right? Going up. But there is something going down, so they cancel out. So they stop going up and just being flat. Because there's something going down, they cancel out. So it's flat, okay? But if they will keep going flat if nothing here, but at this point, it's no longer flat, but because of this going down, so this is also going down, okay? So that black one is the net magnitude phase, magnitude Bode plot, okay? Magnitude Bode. So, all right. So this one is an example. Let's go through another little bit different one. So this one is a little bit harder because it has a pole at origin. It has other 2 poles and 1 0. Okay? So giving a Bode plot paper, can you sketch the magnitude? So, and you may ask, what's the point? Why we do that? Why we do that? So you have a magnitude plot like that. So let's say I have a signal sine omega t put into the system, like with Bode plot like this. I want to tell you. I want you to tell me immediately. If I have an input, it's a sinusoid. Its magnitude is 1. Okay, magnitude is 1, and its frequency, say for example, is 10. My frequency is 10. Okay, 10. Omega is 10. Okay. Magnitude is 1. My omega is 10. Then output, I want to know what is my magnitude. So you will know that your magnitude is the input magnitude multiplied by this magnitude. So this is 10 to the power of 2. It's 100. Output will be 100 sine omega. Is this correct? No. You need to check the phase. So you need another phase plot. You need another phase plot. Okay. I'm going to learn. Well, I'm going to learn magnitude plot first. So let's try something a little bit more different. So let's do, again, you do individual term. Can you see what we are doing here? We are trying to make this thing standard form. meaning the constant term is 1, and this one is S divided by Z or by P, okay? Why we do that? It's because then everything will start from 0 dB, understand? Because let's go to minus infinity to 0 log. So when S is very small, close to 0, then everything will be 1. Then log 1 is 0, so we're starting on 0 dB. So we always start on 0 dB. So either way, it's 0 dB. That's good. Okay. So by doing that, you are doing so. This original form, turn this form, write this way. Okay, you didn't change it. You just add together 100. 100 corresponding 40 dB, right? 100 dB. So first term, we know that this is corresponding to a pole at the origin. So you pass through the 0 dB line, and this is 1, omega is 1, okay? Omega is 1 and 0 dB line. So that's for this one. So how many terms? 1, 2, 3, 4, 5. We have 5 components, okay? 5. So this is the pole at, so this is, you can see 0.5, 20, and 40. So when you go this way, you will see the 25 first, then 20, then 40, okay? So we check this pole for 0 first. So you can see this type of thing was starting from 0 dB, and at this corner frequency 20, then they are going to ramp up with a slope of positive 20 dB per decade. Okay? So that's a pole at Z is 20, Z1 is 20. So you have another 2 poles, Y is set to 0.5. It's all 0 dB, then hit 0.5, then you go down, it's minus 20 dB. And then your omega going up until 40, you will keep all the 0 dB until you see the corner frequency 40. Then you go down minus 20 dB per decade. Okay? So then we are going to add this together, these 5 components together. We are going to see this. Okay, I want you to look at this one carefully. So again, you go from omega is 0, okay? Then you have a 1 over S. It's a pole at the origin. So they will pass this line. It's a 0 dB 1. Okay, this is a 1. Okay, 0 dB 1 point, and this slope is minus 20 dB per decade. Okay, minus 20 dB per decade. So as the omega goes up until 2.5. Remember, this is 1, this is 0.9, 0.8, 0.6, 7, 6, 5. So this is the 5. So this is 0.5, okay? This is 0.5. Until you see the 0.5, okay? 0.5. What are you going to have? Okay? Because 3.5, you have orange like this. So it's minus 20 dB. So in other words, this black line from the beginning, if nothing else, it will be like this one, keep going this way. However, because of this orange color, so then at this corner frequency 0.5, it will have minus 20 plus minus 20. This is kind of minus 40 dB per decade. Okay? Minus 40 dB per decade. And you keep going until you hit this corner frequency. This corner frequency is 20 Hertz, 20, omega is 20. So under 20, then you have going up. Because of the going up, you have minus 40, then add 20, so you have this one is minus 20. This is a minus 20. Okay, minus 20. Then go to then here, you have another one going down, so it's 40. until you can see this is your 40. So this is minus 40 again because of this one. So this overall black one is minus 20, minus 40, minus 20, minus 40. That's the slope, okay? So those corner frequencies are corresponding to the zeros and poles. When you have a zero, then when you have a zero, your slope is becomes smaller. Because zero is positive quantity per decade. So this is how we piece them together as a Bode plot. So the reason we can do this multiplication or adding all these things is because we're using a log operation. So that's why Bode plot is very popular. Okay. So this is you have a constant, you have a zero, and you have a pole, three poles, 1, 0, and again. After you have done the standard form, the gain also changes. Okay. So we only started by doing what? Doing the magnitude. So how are we going to get a phase? So I hope you read this one. I like it. So the plot of the log magnitude versus input is just half of the story. It's only half of the story. You need two plots: magnitude Bode and phase Bode. So we are now learning how to do phase Bode. Okay. Again, I hope you pay attention, and if you can do what we can put on this one here, you understand the procedure here, you will be fine with Bode plot. Okay. So again, let's start by doing this. This too big. Good. So let's start to using the same. We have a zero pole and a pole at the origin. Okay. J omega is the S. So how we can draw the phase angle associated with this function? So we can see that everything is. Let's assume everything is a complex number. So we want to see what's the complex number of the phase angle of this one, phase angle of this one, phase angle of this one. So basically we need to do a phase angle of this whole thing to add. So this phase, add this phase, add this phase, minus this phase, minus this phase, minus this phase. Okay? Okay. So I hope you know that. Okay, I hope you know that. Why this is the case? Do you understand why this is the case? Do you read it? Do you want me to explain to you?
Yes.
Okay. I think it's a good idea. Let's slow down to solve this problem. So basically, we are asking a question like this. I have a complex number z1 and divided by z2. Okay, why we can say the phase of the overall division can be written as the phase of z1 minus phase of z2. Why? This, how many of you can explain this? If you don't know this one, then you have trouble, right? So then let me show you that Z1 is like a real part of Z1 plus J, and imaginary part of Z1, okay? Can I can write this one, right? Z1's real part, imaginary part, and times J. J is minus square root of minus 1, right? So this is a complex number. This is Z usually is a complex number, okay? Then divided by Z2 is RZ2 plus J, imaginary part Z2, okay? You don't see this phase angle very clearly, but if I write in the polar form, this can be written as the magnitude, okay, of Z1, J, the phase angle of Z1, okay, phase angle of Z1. In other words, you heard about this A plus IB equals a Z is a complex number, and this complex number is written as magnitude of the Z times EJ theta, okay? No, I theta. And in this case, your magnitude is what? Is it? What is this theta? I know that tangent theta is B divided by A. Huh? So you have an imaginary axis, real, imaginary. So you have here, which is A is real, B is, so this is A plus IB. So that's a complex number, and this can be written as, from here, this is Z, so from 0, 0 here, and this is called magnitude, or mode, okay? So this is, of course, it's a square root of this one here. But what is the angle here? Angle here. So this is the theta. This is the theta. Okay? But you know that tangent theta is B divided by A. You know that tangent theta is B divided by A. So B divided by A is tangent theta. Okay? Okay. So then we can write, this is the theta, this is the magnitude, so this is Z2, EJ, angle Z2, right? Z2. Okay? So it's a theta 1, theta 2. Okay? Now. Z1, Z2, okay? It becomes magnitude Z1, magnitude Z2, EJ, Z1 minus Z2, right? Minus Z2. This one divided by this one. So that's why the magnitude of that is this, and the phase is the difference, okay? Phase is the difference. Clear? Yes? Clear? Clear? The material I asked you to read of chapter 00, there is a section about complex number operations, okay? So this is supposed to be there, and those supposed to be covered in high school. If you didn't learn this one in high school, you went to a fake high school. Yeah, it's being recorded. I'm correct. Okay? Don't tell me you didn't learn that piece in high school. I don't want to learn that fact. Okay? But now, you see the phase minus, so this phase, what's the phase of a constant? 0. Okay, great. So now this solves the problem, right? So then let's start to. So if you have a constant, the phase is. If you have a 0 at the origin, meaning you have a s in the numerator, s divided by something, 0, okay? It's a s in the numerator, then you have a constant. Okay, you have a constant. And it's 90 degree, okay? 90 degree. Let me tell you something that you should be careful. So I have a j omega here. What is my amplitude of j omega? Don't feel very scared about it. This one is 1, okay? This one is 1, okay? This one is 1. So this is a omega, okay? But what is the phase of this one? The phase is like, it's called B divided by A. A is 0. So I have tangent arctangent of this infinity. 0 put it here. 0 put it here. That's the infinity. So what is arctangent infinity? What makes this one infinity? Sorry, what makes, so what angle, in other words, what tangent of what is infinity? Tangent of what is infinity? So let's do this. This one divided by this. When I increase, go this way, then A will go from big to small to 0. So when I go to here, the A is 0, then it's 90 degree, right? 90 degree. So this is 90 degree. So what is the phase of this j omega? 90 degree. Okay. I hope you start to connect those things in a visual way. Okay. Okay. Don't try to memorize it so hard. No, that's no use. You should understand it. You understand it visually. Understand it. I'll draw with you next after this. So if you have a transfer function in the numerator, you have s, then your phase will be just a constant 90 degree. The same thing if you put on in the numerator, it will be minus 90 degree. Okay? So you have something here. So s, this is called, you have a 0 at the origin. But if you have some s in here, it's called your pole at the origin. Okay, at the origin. So then the phase is 1 minus 90 degree. In the numerator is 90 degree. Okay? So that is easy. This is not. Okay? So let's assume you have a 0 in numerator. This is in the numerator. When I say when I use z in here, that means this thing is in the numerator. When I use a p in here, this is in the denominator, right? In the numerator, so let's say this is 0.1, okay? This is z, okay? So you have a z in here. How you should draw? Okay, this is very important. How you should draw the phase? The phase is you have z. This is your z. What you should do is you look forward. Say 1 decade. This is 1 decade. This is another decade. Okay, another decade. Then you draw 90 degrees at that's 10. That's a 10 z1 here, and 0.1 z1 is 0 degree. So this is 0 degree. This is 90 degree. In between, you need to pass at this 1 z1 point. Okay, then this point is 45 degrees. Why? You did ask. Why? Okay, when I was a student, I didn't know that. I tell you, I didn't know that. So now I learn how to ask why. Just ask why. Why 45 across that point? The answer is surprisingly easy. Okay. The reason is, when you put omega as z1, what do you get? It's 1 plus j. What is 1 plus j? It's square root of 2e to the j 45 degrees. Huh? You agree? You don't? You should. So it's square root of 2 cosine 45 plus j sine 45. So what is a cosine 45? Do you need to check? You should memorize this. So this is square root of 2 divided by 2, square root of 2 divided by 2, okay? So you have square root of 2, so you get 1 plus j, okay? So that's why you have 45. That's why you have 45. Here, corresponding to omega equals z1, at this point is 1 plus j. Okay? This is very beautiful. Okay, I didn't realize when I was a student. So, a few years, not 10 years back, so challenge myself how to explain it. So that's the case. That's the case. Then, of course, if you show up this one in the new denominator, it's the same idea. Same idea. So basically, you need to look a decade down and a decade up. So this is original omega here. Decade down, 0.1 p1, 10 p1. So a decade up. A decade up, starting from here, is minus 90. This is 0 degree. Then this passing minus 45. So again, this is 1 divided by 1 plus j. 1 divided by 1 plus j, okay, is this one, and this is the minus sign, okay? So then we are almost ready to do a lot of interesting things. So we are going to complete the Bode plus for the previous example. So then this is the first example. This is only a pole, only one pole. So by doing that, you are going to see what we have. So at the corner frequency is 50. Below 50 is all 0, but I have a minus 40 dB here. So starting instead of from 0, if I don't have this one, it's only 1, then it starts from 0 dB. But this is 0 dB minus 40 dB, so I start from minus 40 dB until I hit omega is 50. At this point, I go down. So this is my magnitude. But remember, when I have a corner frequency 50, then I should correspond to minus 45 degree. And so I'll, because the constant will give me what? They give me 0 degree. So I still have 0 degree until to this. It's not until to this omega, okay? Corner frequency. It's until to omega divided by 10. And at this point, I know that omega times 10. This is 500. This is 5. Okay, starting from here, minus 90. But in between, just connect these two dots. It will definitely cross this minus 45 degree. So that's the blue one is magnitude Bode. The red one is my phase Bode. Okay. So do you understand this one? Any question is? Do you have a question? This is very fundamental. If you don't know this one, then you have trouble. Do you have a question on this?
Well, I have a question for the magnitude. When we do the magnitude,
Yes.
do you want us to just leave it with the black line on the place, or like?
This is my cake. You only have one. You lump everything into one. Okay?
So yeah, on the quiz itself, you want us to leave the dash lines?
Yeah, it's better to do one by one than add together. Yeah. You can try, but don't worry. I'll lead you out. I'll lead you to do it. Don't worry. Feel me. Let's run through the next example. So we have seen this tuple 1, 0, okay? So we explain how to do this Bode plot. Then what's the phase? The phase is also doing the same. So I'm not sure it's clear for you. So you can see the x-axis is the same. X-axis is the same, okay? Exactly the same. So that black one is the overall phase plot, okay? Phase plot. But to make sure we know it, let's draw a phase plot, okay? So, do you see my hand? Yes, you can see my hand. So, maybe we do this all off so you can focus. So please look at this orange one. Okay, this orange one is the corner frequency is 5. Okay, it's this term. Okay, it's this term, the orange one. Do you read the orange one? This one, 0 dB to 5, then minus 20 dB per decade. So this one corresponding to minus 45 degree. And you do 50, this is 50, this is 0.5. So you do this, so this is minus 90. So, and this red one corresponding to 0, the constant. So you have this one, you have this one, you have S in the numerator. So this is this term, okay? And this S will give you 90 degrees all the way constant. So how about this term? This term will give you this one. So this is the green one. This is the green color. So the green color, this is the corner frequency, is corresponding to minus 45 degrees. So you should see 1 decade here, 1 decade here. So 0 here until here, and then you have 8, you have minus 90 here. So then you start to add everything together. For first, so starting from 90 degree, it's constant 90 degree. However, I have something dropping, so I also drop to the point. Okay, drop to this point. Okay. I will continue to drop. I drop to this point, but this one is a minus 90 already, so this cancels out. So I keep dropping until to the point of minus 90. Okay, minus 90. And again, remember this minus 90, this is minus positive 90. They will just add to 0. So that is this example. I think there's another example. I invite you to take a look. Okay, take a look. Or I already explained about this Bode plotting here and the phase. You guys can continue to work on it. And I'm going to do. Image mute. Screen up. So we are working on this one. So we start about 10 minus 10. So this is 1. This is 0.1. So this is like 10. This is 100. Okay. 100. So then we say this is let's say this is 0 dB, 20 dB, 40 dB, minus 20, minus 40, okay, minus 40. So what I have here is s plus 1 divided by s plus 10, okay? So this should be turned into s divided by s plus 1. S divided by 10 plus 1. So then you should pull out a 10, so this is a 0.1, right? 0.1. Okay? So when I pull in 1, then that means I have a minus 20 dB already here for this term. But for this one, so this is a 1, this is a 10, so let me mark it. So this is a 1, this is a 10. So when I omega from log 10 omega, I go from 0, that is minus infinity, 0 and to here. Everything is 0 dB. Everything is 0 dB. Okay? Until I hit this 1, that is s plus 1, then I'm going to go. So this is here, this is 1 dB here, so I'm going to connect this one. So this is 20 dB per decade slope. So this one will go all the way up. So this is blue. So this term is blue. Okay? Blue. Then, how about that? So I'm going to have this term is red. Okay? So then the red one is also 0 dB all the way until I hit here. Then this is so minus 20 dB. So this is 1 decade. So this is minus 20 dB per decade. And you hit this one, I keep going to infinity. This is a 1 line, okay, 1 line. Okay? And how about this one? This guy is minus 20 dB. So this is, let me do another color. This green color. Okay, so this is a green. Green. So these 3 lines, red, blue, red, and green, will add together. And you see the color. So for now, yes. The resultant one is black. Can you go with me how to do this black? And also draw your stuff on your quiz. So you can see what I identify first, what I do next. There's a logical flow there, right? So I also scan from 0 to 0 hertz. So that's the so from here everything is 0, but everything is 0, but you need to do this. So everything is minus 20 until here. So this one will go up, then I will also go up, right? So I will also go up. So this is also go up parallel to this one, right? I'll keep going up, right? But until I hit this one, then you go up this 20 dB per decade, I go down also 20 dB per decade, so this one will cancel out. Add together is 0, so I'll hold at this one, right? I'll hold this one. So this black one go to infinity. This black one, this is my Bode plot. Sorry, this black one is my Bode plot. This constant minus 20 dB, then going up 20 dB per decade, then go flat again. Make sense? So you need to mark those essential ones, like this is a 1, this is a 10, those are the corner frequencies. Corner frequencies. Or some people say this is a critical frequency. Okay? So now let's do phase, okay? So let's assume we start from 0 degree. This is 90 degree. This is minus 90 degree. This is 45. This is minus 45. Okay. So what I'm going to do is do in the green. Okay. For the term, the green, this guy, what is the phase? 0. So it's 0. So this is the green, okay? This is 0. So what is the phase of this guy? No, it's easy. We check its corner frequency. This is 1, okay? Then we need to check about its 0.1, okay? And also check about 10, okay? We know that this 1 corresponding to 50 degree, and this 10 corresponding to 90 degree. And we draw the 90 degree. Oh, I should use blue, sorry. I should use blue, okay. So let me use blue. So basically I have 90 degrees, the little 90 degrees, but at 1 is 45, and this one is 0. So it's 0, this is a straight line passing 45. So this is my blue, okay? This is my blue phase portrait. How about this one? So when S is 10, so its denominator, 10, I know that it's corresponding to 45 degrees in here. 1 is corresponding to 0. Then I need another 100, is here, 100. So this 100 will correspond to my 90 degrees. So everything will go, oh no, I need to use red. Sorry. So I need to, this is minus 90 to infinity all the way. But I start from 0 degree all the way until I hit 0.1 of my corner frequency, that's 1. Then I pass the minus 40, pass again to 90. Okay? Red, green, blue. Now let's check the black. So what's the black? Black is like this. So my phase is always 0, 0 until here. Then everybody else is 0, so I go here, right? Until to here, I find out I go this rate and he go this rate, so then I'm going to keep constant until here, okay? Or keep constant until here. And then, but this is still going down, but this is not going up anymore, so it's a flat. So which means I need to go down, okay? I need to go down. This one parallel to this, and go down. I'll keep go down. I'll keep go down. Because this one and this one cancels. This one and this one is 0. So, and this one will keep going down. Is it? It will be 0. No, sorry. This will be 0. So it will be 0. Yeah. Because otherwise, these two add together is 0. So the black one is 0, going up, then 0 again. So you can see, this thing will give me some phase lead in certain frequency range, phase lead. So this is actually a lead, phase lead, okay, phase lead filter. So I can call this guy a phase lead filter, because I make the signal when you pass to this filter, its phase will got a little bit positive shift, right? Will never become negative. It just always phase lead or lead it. Okay, it's called phase lead. Okay, phase lead. But what is phase lag? What is the phase lag? That's simple. You swap this one. The position swap it. It's become phase lag. So in control, this is called compensator. I make the system purposely phase lead to achieve something.
For phase lag, is that what did you switch?
If you do face lag, you swap these to this one. This is 1, this is 10. Okay, this is face lag. Okay. So that's why body plot can give you very good insight about what. So now from this black one, we know this is face lead. Okay, it's face lead. So give me back your face. Then you can go home and have a productive weekend. Okay? Get a lot of work done. Put your name in there, and I hope this body plot will solve your basic body plot requirement. Give me back your face, then you can go home. Thank you. Thank you.